We all know gravity. It is the force that makes apples fall to the ground and planets go around the sun. And we all also know that atoms, protons, electrons, and other subatomic particles are quantum and that they are guided by the Schrödinger equation. But is gravity also quantum? We don't know yet, but thanks to the combined efforts of theoreticians and experimentalists at Leibniz University Hanover, we will soon find out. So this is what we know about quantum gravity so far. In some experiments, where everything moves reasonably slow, so they are non-relativistic, and where matter has no observable quantum properties, everything is guided by Newton's laws of motion. And there are several theories of quantum gravity that were proposed, such as string theory and loop quantum gravity. And these theories over here, we don't have any experiments to tell us which of them is the correct one, and they are relativistic and quantum. But we can perform a non-relativistic limit of those theories and obtain a phenomenological theories of quantum gravity, which are non-relativistic but still describe how gravity influences quantum matter. And then we get these cone of theories that somehow describe as quantum and relativistic, quantum and non-relativistic, and non-quantum and non-relativistic. Now we know that at the bottom there is only one correct theory, because that was already discovered by Isaac Newton. But there are also several phenomenological theories of quantum gravity that were proposed. And our goal here at Leibniz University Hanover is to perform an experiment that would find the correct one. And by doing so, we will also significantly restrict all possible theories of quantum gravity, because then only those ones that have the correct phenomenological limit will be admissible. The problem with designing such experiment is that many of these phenomenological theories of gravity can give you the same predictions in a given experiment because of their classical limit. So we somehow need to design an experiment that does not measure the classical limit, but actually measures the differences between these theories. And for that, we will use an atom interferometer. An atom interferometer is a device that takes an atom or other quantum particle and makes it follow not just one path or not the other path, but makes it follow both paths in superposition. So it in some sense follows both paths at the same time. And then we place external masses around this atom interferometer, and we actually need two of those masses, because once the atom is following the two paths in superposition, the masses will start exerting gravitational interaction with the paths, and they'll start rotating them, or to be more exact, causing phase shifts. And once the paths recombine, we can measure the relative phase shift, and from this we will learn the correct phenomenological theory. And the reason we need two masses of different shapes and sizes is because then we can design the experiment so that the classical interaction of this mass exactly cancels with the classical interaction of this mass, and we will observe only the quantum effects of gravity. And the only thing we need for this is somebody with a very large atom interferometer.
Hello, and welcome to the very long baseline atom interferometer facility here in Hanover. We research how those atoms interact with gravity at the individual atom level. So we grab onto a bunch of atoms with our lasers, and then we toss them upwards and let them fall. And through this process of free fall, these atoms evolve through time, and then in the end we take a picture of them that gives us information of how they fell. The new thing that we are doing here is adding a small amount of an additional tungsten mass and researching how this amount of tungsten mass influences the atoms through gravity.
The experiment in Hanover has two distinct outcomes. The first one is that we observe deviations from Schrödinger equation and that we find some new physics. The second possibility is that we prove that a single atom interferometer is correctly described by a Schrödinger equation when influenced by external gravitational sources. While the second possibility is more plausible, in this case we will actually indirectly prove that gravity is quantum and that gravity-mediated entanglement exists. Gravity-mediated entanglement is an experiment that was first proposed in 2017. And the idea is not to take one, but two atom interferometers. So this is the first one that we had before, and we will also have a second one over here. And now what happens is that we'll have a quantum particle in a superposition here and quantum particle in a superposition here. And since they'll be close to each other here, they will interact gravitationally. And their mutual gravitational interaction will cause a phase shifts that will cause these two atom interferometers to develop a very specific type of quantum correlation called entanglement. Entanglement is one of the fundamental resources in quantum information, and you need it, for example, to violate Bell inequalities, but also for quantum key distribution. But the fundamental result about entanglement is that it cannot be created via classical interaction or via local operations and classical communications, also known as LOCC. So what happens is that if these two interferometers get entangled because of their gravitational interaction, then gravity cannot be described by a classical field theory, because that would violate the LOCC principle that cannot create entanglement. But the problem is that, strictly speaking, we don't know what physical laws guide the interaction between two atom interferometers. But what we find out is that if one of the interferometers would not be in a superposition, but localized just in one of the arms, then this would essentially act only as a localized external mass, and then we know what happens. And the same thing would happen if it would be localized here, or if the other interferometer would be localized here and here, while the first one would remain in superposition. Using this idea, we find out that we know something like 75% of the free parameters guiding this interaction. But we still need to find the remaining 25%. But here, quantum information comes to the rescue, because by requiring some reasonable assumptions, such as that all probabilities that we can observe after the experiment ends are positive, we get that we can uniquely compute what are the remaining 25 parameters guiding the interaction. And then, if the experiment in Hanover verifies Schrödinger equation for one atom interferometer, we find out that also it holds for two atom interferometers, and hence their mutual interaction will cause gravity-mediated entanglement, and gravity is quantum. So the experiment in Hanover will have two distinct outcomes. Either we find new physics, or we prove that gravity is quantum.